So hello everyone and welcome to my presentation. So my name is Mahsa Noroozi and I'm presenting the work that we've done together with Markus Fiedler, and we submitted for ICC and it was accepted for this year. And the title of the work is a MEM+ model of age of information with worst case and statistical bounds. And we are part of the Institute of Communication Technology from the Leibniz University, Hanover. So first of all, about our motivation. So at the Institute, we're working on different network cyber-physical systems. You can see two examples here. On the left side, we have some tracks in vehicular communication that they send some update messages, some feedback together. And on the right side, we have a robotic arm. And I'm also basically working on this area. And it's also network control system. And what this actually is, the network control system, it's a physical system that is connected with the cloud or some servers. And we control these physical systems through cloud or servers through internet. And as I said, so we get the sensor messages from our physical system, for example, robot arm, through the internet or feedback channel. And as the name will be the feedback messages, and we set the control messages through internet again, or through network to our physical system through forward channel. So these update messages are the timely status updates that we get from remote sensors. And the sensors, for example, of a robot arm should be position of the robot arm or the hand or external cameras. And this information are important, how fresh these information are. And the freshness of status information that we get, because it's through internet or through network, it depends on the network delay that we have or the update rate of the sensors. So we give a name to this freshness of information as age of information. And you can see here a figure. And in this figure, we have T sub A of n is the arrival time from the sensor update that we have to the network. And T sub D is a departure time from the network to the sink. And you can see here the arrival time of the first packet. And that time, that's the packet is generated. And the age of this packet is growing up with the time linearly. And at this point, the departure of the first packet that we have, still the age is growing up. So now we have this packet, and until the second packet arrives. So you can see here the departure of the second packet to our sink. And now we have a decrease in our age of information because we have now the second packets, then second packets is more fresh. And here we have the formulation and the expression of the age of information, and we call it as delta of T. And as you can see here, that we find the departure time of the last packet, and the delta of T, or the age of information, will be the actual time minus the arrival time of these packets. So there are many works in age of information, queuing theoretic, that they consider optimal update rate in different areas in periodic or random updates. And in different models, for example, wireless channel models. And there's also a good recent survey on age of information in JSEC from Yates et al. And related to network calculus, we have also two related work for multi-user and multi-hop systems. And the first one is the multiple, the work from Papas that uses network calculus for fading channels and derives statistical delay bounds. And about multi-hub first-come first-served systems, there is a good work from Champati that uses max plus algebra to derive statistical age of information bounds. But in our work, we will use min plus algebra. And I will here introduce the difference between max plus and min plus algebra in this slide. On the left side, you can see a model of the max plus, and on the right side, a min plus. So the max plus here uses packet timestamps. So you can see here, T sub A of n is our packet timestamps of the arrivals. But in min plus, at the right side, we use a cumulative arrival function. That's the A of t. So max plus algebra is actually useful for delay metrics. It's easy to find the delay, for example. That is just the departure time minus the arrival times. But for min plus algebra, it's a bit more complex, more evolved. And you can see also the expression of the delay here. And in the figure, it's easily to find that the max plus is pseudo inverse of the min plus of the left side. And there is a duality between min plus and max plus that you can find it in the book of Liebeherr. But the min plus algebra has this advantage that we can use the min plus to model multiplexing, scheduling, and wireless channels. Here I will define the age of information using min plus. So first for the formulation, so for delay, it's an infimum of the variable that the departure time is greater than the arrival time. But maybe instead of explaining the expression, I just explain in this figure. Maybe it's simpler to understand. And here, for example, for the delay at time 3, we have to look forward. So at time 3, we have 2 packets that are arrived. And we have to look forward into the time and find the departure time of the second packet. And this interval is our delay. But in contrast, for age of information, we have to look backward. It means, for example, if we want to find at time 8 the age of information, we have 2 packets that are arrived, and we look backward and we find the arrival time of the second packets. And this interval will be our age of information. So now in our work, we use lossless time variant conserving system. And as you can see, we have the cumulative arriving bits on the left side, the arrival function, and the departure function, DFT, the cumulative bits that are departed until time t. And we have a buffer and a service process that's S of tau and t, and it's available service in this time interval. And you already probably know this formulation. Oops. That the departure is always greater than or equal to infimum of the summation of the arrival and the service process. So now we want to use this formulation and define the age of information. So we substitute this expression into the age of information, and we use this expression for the arrival. And then we get this expression in the bottom. Maybe it's a bit difficult to understand, and I try my best to explain about it. So, and I will not prove this formulation here. It's hard to explain it in our presentation. So here we have the age of information. It will be the supremum up to infimum. That should be less than or equal to 0. The important part is the supremum and this part that is less than or equal to 0. And what does it mean? We want to find when do we get the higher age of information. So if we have 2 less service, then it means if you have 2 less service in the first part or the second part, then because it's a supremum and it's less than or equal to 0, we have higher age of information. And how about the arrivals? So in the first part, in this time interval, we have the minus arrivals. And it means if we have too many packets that arrive to our network, then we have the congestion. And this congestion delays, it causes higher age of information. And the second part, in contrast to the first part, now we have the plus arrivals. And in this part, it means that if we don't have too many updates, then we have to wait for new updates. And it means, so we have to wait, then we have the idle waiting. And it causes, again, higher age of information. So now we can see this effect in our results. So here we have a deterministic channel with random updates. And we want to drive statistical age of information bound. And this is the probability that the age of information is greater than or equal to, greater than a threshold, delta of epsilon, that is less than or equal to a small value like epsilon. And epsilon here is 3 different values, 10 to the power of -3, -6, and -9. And in the x-axis, we have the omega in milliseconds, and omega is our update interval. So it means we have the mean update rate 1 over omega, and our link capacity is C. So now you can see here easily about this expression that I explained. So on the right side, we don't have too many updates. So for large omega, it means we have to wait for the new updates, and we have the idle waiting. So the age of information increases. On the left side, now we have too many updates that we have the congestion, and again, the age of information grows. And here we have another model. It's a Markovian on-off channel, and we have periodic updates. And here we have also the delay that we show. But for age of information, as you can see, it's similar. That's again with higher updates here in this area, that the age of information is going up, and again with too few updates in this area, the age of information is still going up and increases. But for delay, at the beginning, it's similar to age of information. So we have too many updates that we have. And on the right side, it's going to be constant at some point, and that is due to the channel outage. And here, as I said, we get the advantage of the min-plus model, and we use multi-user Markovian on-off channel with priorities. And what does a priority or this number or this values means? So M means that we have this number of higher priorities. For example, if M is equal to 10, it means that we have 10 users of the higher priority, and we look at the age of information for the user 11. It doesn't have higher priority. For m equal to 0, we had it also in the last slide, but for the other users, for the other number of users, you can see that at some point on the right side, it's going to be stable. And you can see here that this model is a really good model if the load is moderate. And that's because of the statistical multiplexing gain, and because the phases of these channels are independent. So now I will conclude my presentation. I introduced a min plus model of age of information for periodic and as well as random updates in different systems with random services, for example, wireless channels, and schedulers with random cross traffic. And as I said, we can get the advantage of this model and extend it to multi-hop networks in future work. So thank you for your attention. If there are any questions, we'd be happy to answer. Thank you.
Thank you very much. Yeah, we do have time for questions, so we have perfectly time. Lossless, please go ahead.
Hi. So I just have one question. Why the min plus and the max plus was more natural to this? What is the advantage of that? I mean, even with max plus, you can do what you're saying. Still need to come to answer. So what was your motivation?
So
you may want to first repeat the question.
Yes, please repeat the question.
So you mean the advantage of the min plus against the max plus algebra. So the motivation actually was that we can use it for multi-hop networks or multi-user and wireless channels. That's it's simpler to use the min plus model against the max plus.
You can still do max plus. Is there another like?
So the priority, do you have a leftover or kind of yeah, and then max plus you're out of luck.
So there is
that's the
multiplexing leftover service.
So you have two choices. You have either a bad delay computation in min plus, or you have a bad leftover service curve in max plus. Looks like min plus is less leftover, max plus leftover service curve is terrible. Because you cannot really add or something. Sorry.
Yeah. No, it's open for discussion, so please be free to ask and contribute. Yeah, please.
Properties about age of information are there. I think that can be said also from that deterministic perspective. There is any problems with deterministic approach?
Say again.
If there is, so the talk was about a stochastic analysis of age of information. So
we had also a deterministic channel. So we had also here a deterministic channel. Or
If you go to the slides where you explain the three terms.
oh, okay.
So if you go for deterministic, then this is t minus tau, and this is t minus delta minus tau. So it just is not a function of two variables, but the difference.
Okay. So it's just a reduction of the problem.
Yeah. Yeah. So it's a special case of the problem.
Okay.
That's fine.
Yeah.
So if you want to compute the range of information, you will need end-to-end service. You cannot use like TFNI techniques. You will require the end-to-end service to find out the end-to-end information.
Cannot really hear you.
But the range of information is defined with the end-to-end service field from the flow of interest. it's a relation between your A and D, but it's like end-to-end. You cannot like analyze server by server.
Oh. So the question is, could you do a hop by hop page of information analysis?
Oh, okay.
So you get the age first. And then, well, that's an interesting question. So we haven't thought about that, or I haven't. So you mean like summing up delay bounds for each individual element? Would there be something similar?
Yeah, but the thing that you're coming after the operational approach, I will have computed the end-to-end latency, so you require to not TFA like the PMO like.
You have to take like the worst.
Yeah. So summing up age of information on a per hop basis may or may not work. So, yeah. But it's nevertheless interesting to think about. So, all right. So, Hanover, please go ahead. We have time.
We have time. Okay. It's rather a minor question, but systems that are built to optimize age of information try to diversify paths, for example. So if I have replicate packets and sending multiple paths, do I include this in this model?
You mean if you duplicate the packets? You could also use it, I would say. Or you mean?
It's probably then worth looking at.
Yes, this is the MGF. This is the MGF.
So what is the expression in there?
It's we can give you the link to the paper. So that's okay. And there is the MGF expressions. Yeah. All right. So let's take your suggestion also offline. And thanks again for the presentation.
Yeah,